Hello and welcome to Parul University webinar under IST student chapter. Today we have among us Dr. Tejal Patel, Associate Professor from GSET. Ma'am has more than 20 years of teaching experience and 7 years of research experience. Ma'am has also published 10 papers in international journal and also have several other papers at conference proceeding. She is also a member of various professional bodies organization and is a principal investigator for the Guj Coast MRP project with specialization in membrane separation technique. So on behalf of Parul Institute of Engineering and Technology, Diploma Studies, Chemical Engineering Department, we welcome you, ma'am.
Thank you. Thank you so much, ma'am, for
Yeah.
nice introduction.
Thank you. Welcome, ma'am. And now we can proceed with your session, ma'am.
Yeah, sure.
So I'm stop presenting. Now you can present it.
Okay.
मैम ऊपर से मिनिमाइज कर दीजिए.
Okay.
हाँ.
Right. Okay. Good morning, all of you. Today, as madam said, right, actually we are doing, my research is in membrane separation processes, but looking into the students range, wide variety of students, means the level wise, I have included only just overview of all the membrane separation processes. Am I audible, madam? Is it okay?
Yes, ma'am. Yes,
okay.
ma'am.
Okay. Then let's start with the subject only. What is the difference? Membrane separation process is how it is different from the conventional separation processes, right? So if we just say how it is different from the conventional separation processes, these membrane separation processes are known as rate governed separation processes and not equilibrium separation processes, because whatever we have studied in our mass transfer, right, mechanical operation, mass transfer, all unit operations we have studied, that we study that all they are based on the equilibrium. Either it is distillation, extraction, absorption. They, once they reach to the equilibrium state, then separation is not possible, or no further separation is possible in that case, right? So, but these membrane separation processes, they are rate governed, means there is no equilibrium is established based on difference in the driving force. Either there are maybe temperature difference, there may be pressure difference, there may be the concentration difference. So based on the driving force, the separation is taking place, and it will continue until there is a driving force between the feed side and permeate side, or between the two sides of the membrane, right? So it is known as rate governed separation processes, and driving force may be pressure, concentration, temperature gradient, or electrical field, right? Okay. So what is membrane? Now this membrane is a Latin word, membrana, which means skin. We have in our body also we have a membrane, right? Kidney, what it acts like a membrane only. It will purify our blood. So this membrane, even wood plants, they have this membrane. They allow only some water to wet water to absorb into this and from the roots into the plants and stems, right? But they will not allow any salt to absorb from outside of this land. Same way, membrane is a barrier. Mainly whatever the commercial membrane we are using right now, they are all polymeric, and nowadays because of some limitation they are ceramic membrane, metal membranes, some liquid filled pore membrane. Now there is so much research, but earlier these membranes were made of polymeric material. So this membrane is a barrier which separate two phases, means it is a feed side and there is a permeate side. Means when there is depending upon the concentration difference or pressure difference, the feed is allowed to pass through this membrane, and this membrane will allow only some specific uh, species to pass through it depending upon the characteristics of membrane, and these membranes mainly identified based on their pore size. Their pore size, they depending upon the pore size, they will allow the solute, or they allow the uh, solute or any feed solute or any solvent to pass through it, right? Solvent can easily pass through it, but the solute will allow to pass through it based on the pore size of the membrane. You can see in the figure there is a bigger molecule, smaller molecule. Membrane is such that it will allow only the small molecule to pass, and the bigger molecule will be rejected by means of the membrane based on the pore size of that membrane, right? So if we just see the classification of all the membrane separation processes, they are based on their driving force and membrane separation process. If I say that the membrane is up to 1960, they all were at the laboratory scale. All the membrane separation processes, they were at the laboratory scale or under the research. But after 1960, the Loeb and Saurirajan, right? Saurirajan is an Indian scientist, MSU alumni. So that Saurirajan, but he's working in Germany, right? So this Loeb and Saurirajan, these two scientists, they have made asymmetric membrane, cellulose acetate asymmetric membrane, which have very high strength and flux. Strength means when you want to apply very high pressure to come out the solvent from that membrane, right? So at that time, the membrane is, if it is thick, the flux, the permeation rate will be very less. So it will not allow the liquid to pass through it if we have, even though if it is thick, even though we applied the higher pressure. So membrane, according to Darcy's law, membrane thickness must be very small or must be thin, or it is inversely proportional to the thickness of the membrane. Membrane thickness will also give one resistance to flow to the liquid. So thickness should be minimum, thickness should be very less, and when the pressure driving force is high, this membrane will not uh, tolerate that much amount of pressure, right? So it will damage. It will the structure will not remain same. The pores may open, right? That so after this, Loeb and Saurirajan, they prepared asymmetric membrane. After 1960, all these membrane separation processes are commercialized, and up to within these 2 decades, means from 1960 to 1980, all these membrane separation processes are commercialized, right? If you just see the inception or the history, then membrane started in at the time of Second World War. At the time of Second World War in 1940, the Germany has the biggest crisis of pure drinking water. At that time, whatever the conventional method available to check the safety parameter of this water, whether it is drinkable or not, it is very tedious and cumbersome. At that time, these membranes come into the picture because they will remove all the TDS, all the suspended solid, all the bacteria and viruses from that. So it is easy for them to identify, oh, this is the filter which can remove all these things, and we can safely drink this water because of lots of air raids, right? Bombarding all the water supply lines, they are damaged with this air raids. So they at 1940 it will come into the picture first time, microfilters. Then 1960, because of so many limitations, they are under the research at the laboratory scale only. And after 1960, and between 1960 to 1980, most of the membrane separation process which is listed out here, they all are commercialized. Not membrane distillation is quite late, but it is also now a commercial technique to separate the for the separation of uh, feed and solvent of any feed or solution using the temperature difference as a gradient. Okay, so let's start with the in my presentation today I will discuss majorly pressure differences, means pressure driven membrane separation processes. Rest it will take very long time if I go for the dialysis, electrodialysis and membrane distillation. So major application of membrane separation process which is widely used in chemical industry, that is pressure driven. I'm not saying that dialysis and electrodialysis is also used. GSFC, their brine production is doing by means of electrodialysis, right? So dialysis, electrodialysis, membrane distillation are also there, but this separation, RO is the biggest membrane separation process in Saudi country, where there is a water scarcity. They, from the sea water, they produce the potable water, right? Drinking water from the sea water. So reverse osmosis is the major desalination, even UF, ultrafiltration, nanofiltration, microfiltration, and parvaporation. Among all, I have listed 5 pressure driven, 1 concentration difference, that is dialysis, electrodialysis, and membrane distillation. Among all, there is no phase change taking place. Only in pervaporation there is a phase change taking place, right? And even membrane distillation. Okay, so now if we just see all the types of membrane separation processes are there. In that, how the flow of liquid, right? This line is the membrane separation, right? This is the membrane on which the fluid is flowing, and depending upon the size of pores within the membrane, they allow some spaces to pass through it and rest retain on the surface of the membrane. So there are 2 types of flow in the membrane majorly: dead end filtration and cross flow filtration. If I say dead end filtration is not commercially used in chemical industry, means not used in chemical industry because we have to process very large amount of liquid. But in small pharmaceutical industry, where they have to separate very precious material, or the very costly liquid separation, and that in that case they go for the dead end filtration, right? The capacity is less, the small volume you need to process, then dead end filtration is used. In dead end filtration, the feed is enter directly impinge on the membrane surface. This is the filter medium, which is membrane, right? Directly come on the surface of the filter, and the vessel is pressurized. On the feed side, the vessel is pressurized, and because of the gradient of pressure on feed side and on the other side of the membrane, permeate side, the solvent will pass through the membrane, and some solute which is smaller than the pore size of the membrane, they can also pass through the membrane. So this is permeate, or you can say it is filtrate, and this is the feed. So slow, after some times there is no reject line, means there is no, it is not a continuous process, it is a batch, right? Once there is a stop, once there is no permeation from the filter or from the membrane, we stop the process. Whatever the solute retain on the membrane surface, we just clean the membrane and again reuse it for the next batch, right? So life of membrane, that will also affect on number of cleaning, how you clean. In either it is continuous or batch process, you have to clean the membrane after sometimes, after few hours of use, because of whatever the solute which is retained by means of the membrane, they remain on the surface of the membrane, means it will deposit on the surface of the membrane, and you have to clean it, otherwise the flux will decline. The flux will decline, or the rate of permeation will be less, right? So any membrane separation process, either it is dead end or cross flow, it depends on, if you just want to check the performance, then it depends on what is the flux, means what is the rate of permeation, how much liter of volume is processed per meter square of membrane area per unit time, per unit hour or unit second or minute, whatever. So it is known as flux, right? So flux is very important, means what, how much volume you are processing in how much liter of liquid or how much meter cube of liquid pass through the per meter square of area and per unit time through the membrane. And second parameter is rejection, which is what is the concentration of solute in the permeate side. Suppose you want to reject, major application of all the membrane separation processes are in industry, chemical industry, textile industry, electroplating solution, desalination. There are n number of applications. So rejection means either in any industry, their intention is to separate the solute from the solvent, or to have the clear permeate, or they want to concentrate the solids, or they want to concentrate the solute within the liquid itself. So maybe depending upon the need, either maybe the reject stream, if I say this cross flow, if the reject stream, that is their desirable product, or maybe this permeate which is coming out from that membrane, that is desirable product, right? So if they want to concentrate, then the stream which is living on the other side of the membrane, that is known as concentrate or retentant, right? That is the desired product. So in cross flow filtration, the feed is coming tangentially to the membrane cross, right? The permeate, the feed and permeate, they are perpendicular directions. Means the feed is coming from this direction, the membrane allow the liquid to pass through it from this direction, and whatever solute is retained on the membrane surface, they retain on the membrane surface. But because of, in most of the cases, because of this solutes, they are rejected by means of the membrane, so they will leave with the reject stream from the second side of the membrane. This leave from with the reject stream, but some solute will deposit on the surface of the membrane, and some solute will be deposited on the membrane surface, and because of that, after some times of use of membrane, there is a accumulation of solute on the surface of the membrane, and this accumulation, in case of membrane separation processes, it is known as concentration polarization. Means there is an increase in concentration of solute at the membrane surface, and because of increase in solute concentration at the membrane surface, it will reduce the flux, because now this whatever the salt which is deposited on the membrane surface, they may create, if they are inert, then there is no problem, but they may interact with the membrane surface and cause the fouling of the membrane. So fouling is the major problem of any membrane separation process. That fouling of membrane means membrane will foul because of deposition of solute on the membrane surface. And the secondly is that flux decline, and because of deposition of solute and active membrane area is reduced, and because of that, there is a decrease in flux. So flux decline and concentration polarization, that is two major problem in membrane separation process. So there is a dead end and cross flow. Most of the industry applications, they use cross flow membrane filtration, right? Now, if we just see the pressure driven processes based on size range of feed solutes, right? This is the pore diameter, and see, you can see the microfiltration, ultrafiltration, and reverse osmosis. Nanofiltration is in between UF and RO, right? So this nanofiltration is known as ultra osmosis. It is loose RO and tight UF, right? So microfiltration, their pore size is between 100 to 10,000 nanometer, right? Then 1 to 100, that is UF, NF, and RO. 0.1 to 1 nanometer means up to 10 angstrom is reverse osmosis. So see what, and this is shows what is this microfiltration can allow to pass through it, right? Viruses will not allowed by means of the UF membrane. Bacteria and suspended solids, other bigger particles, they will be retained by means of the MF, right? Similarly, viruses and proteins are concentrated by means of ultrafiltration. UF, they have major application in biochemical industry for the concentration of protein, for the concentration of cheese whey, hemoglobin, plasma, and all this separation. And the nanofiltration, they can allow, if you just see, they allow multivalent salt to reject, and they allow monovalent salt to pass through it. And RO is such a dense membrane, the pore size is so small that you can say it is simply dense, means there is no pore size, and it reject all type of dissolved solid, all bacteria, viruses, proteins, dyes, everything. Even monovalent salt and divalent salt cannot pass through this. Means sulfates, chlorides, sodium, potassium, and no any monovalent, divalent salt from the water can even pass through the reverse osmosis, right? So that is reverse osmosis. Okay, if I just see that same slide in different presentation, right? Microfiltration will allow water, monovalent ion, multivalent ion, and viruses to pass through it. It will not allow bacteria and suspended solids, while ultrafiltration allowed multivalent, monovalent water, viruses, bacteria, and suspended solids are not allowed. Nanofiltration will allow partially multivalent salt to pass through it. Viruses, sorry, it will reject by means of this, but these two will be allowed. And reverse osmosis, only water is allowed. In reverse osmosis, not shown here, but reverse osmosis allowed only water to pass through it, and all these others are not rejected by means of the membrane. Same, you can here it is written in the with the pressure. With the pore size, in the earlier slide I will show you the pore size. The pore size is bigger, 0.1 to 5 micrometer in in MF, microfiltration. The pressure required is 0.1 to 3 bar, right? 20 to 0.1. As the pore size is reduced, pressure requirement is increased. As the capillary pore size is reduced, the pressure requirement is increased. Here see for RO, the pore size 0.1 to 1 nanometer, almost closed, almost dense membrane. The pressure required is 10 to 100 bar. 5 to 30 bar, it is nanofiltration. 2 to 10 bar UF, and 0.1 to 3 bar MF. Here it again same slide. Suspended particles retained by means of the MF. Selected macromolecules like viruses, bacteria, they are also retained by means of membrane. Then multivalent small and small solute retained by means of NF. Salts, all the salts are rejected by means of the membrane, but water can pass through the membrane. And most of the membrane separation processes, they are aqueous system, but it is not true that it is not used for the non-aqueous system. Nowadays, there are some application in which is also available for non-aqueous system, and that is membrane, by using membrane. So if we just see, these are the types of membrane processes, and the heart of this membrane processes is type of membrane and how this membrane is modularized in that pressure vessel. So you will get the bigger membrane filtration area in a small pressure vessel. Like all pressure driven membrane separation process like RO, UF, MF and NF, they all are driving force is the pressure difference. So how in a small volume that you can, in a small pressure vessel, how you modularize these different modules into the pressure vessel so that maximum membrane surface area you are achieving. But before that, what are the types of membrane? Right, there are microporous or homogeneous non-porous. Homogeneous non-porous means they are dense film which is used in RO. They are dense film which is used in RO, right? These are the dense film where there is no pores can be visible, right? Okay, so this is homogeneous non-porous membrane which is used for the reverse osmosis. Then microporous membrane. Microporous membrane, you can see this, only surface pores you can see. That fully porous. The pores may be tortuous, may be of complete cylindrical pores. They may be highly tortuous, but they are porous membrane, right? Here it is shown the cross section. In some cases, I'll come to this point also, symmetric and asymmetric. These are the porous membrane. So MF, microfiltration, ultrafiltration and nanofiltration, they are using porous membrane. RO is using dense membrane. RO membranes are dense membrane, right? So, and again, this porous and non-porous membrane, they are again symmetric or asymmetric. Symmetrical membranes means they have identical structure and property over the entire cross section. You can see this homogeneous film, right? This is homogeneous film which has an identical structure throughout the cross section, while asymmetric membrane which have a different structure and property, variation across the membrane thickness. You can see this is porous membrane and asymmetric. The pore structure, this is the upper layer, which is porous, these two layers, they are again having different structure. Same way here, means you can see this is the schematic, right? Porous skin, porous skin layer, which actually this layer actually act as a membrane. The rest two things are act as a support. Mostly polyethylsulfone or non-woven polyesters, they are used as a support. And actual porous skin on the membrane, which is actually used as a actually act as a membrane, that is very thin, even 1 micrometer of that thickness, right? The whole thickness of membrane is maybe 100 to 150 micrometer, but the actual layer may be of 1 micrometer, right? Even less than that is possible. So as you reduce the thickness of membrane, the flux will be more, the flux will be high, right? So this is asymmetric membrane. You can see the three structure. These are the bigger pores, then medium sized pores, and continuous dense film or a liquid homogeneous skin layer, right? Porous skin layer or composite membrane. It is also known as composite structure. It is not made up of one single material, but it is made up of 2 3 different materials, and the actual membrane is at the surface of the membrane, which is act as a membrane. This is sponge type structure, means highly porous. It is shown here, right? So asymmetric or symmetric or even porous membrane, there are isotropic and isotropic. Isotropic means having similar pores on the surface of the membrane, and anisotropic means there is a very wide pore size distribution over the entire membrane surface. Okay. Now, these types of membrane, if we continue, then it is porous, non-porous or dense membrane. And third one is electrically charged membrane. This electrically charged membrane means that pores, these are the these are the porous membrane which is used in electrodialysis, right? Porous membrane and dense membrane, they are used for MF, UF, NF and RO. This electrically charged membrane used for the electrodialysis, where the pores carry some charge. Where the pores carry some charge, right? That pore walls carry some positive charge or negatively charged. There is a so this positively charged, if the pores carry some positively charged, during the membrane preparation we allowed some uh, cross-linking of some substances which will give you this positive or negative charge on the membrane wall or the membrane pore wall, right? So this positive charge will ion, if the membrane is carrying some positive charge, then it will allow only the opposite charge ion to pass through it, and the same ion will be rejected. So you can see in this figure, right? This positively charged ion we cannot pass through the membrane, it will be rejected, but the negatively charged ion can be easily passed through this membrane. So the same charge ion is known as co-ions, and the opposite charge ion is known as counter ion. So counter ion can pass through it, co-ion can be rejected. So this is known as Donan exclusion. In case of porous membrane, the mechanism of separation is based on sieving mechanism, right? Sieving mechanism or steric exclusion. Sieving mechanism means the same function as sieve. The particle which is smaller than the pore size of the sieve will pass through it, and bigger than the pores opening of the sieve, they will be rejected. So in microporous membrane, the same principle, sieving mechanism. Particle which is smaller than the pore size, they can pass through it, and particle bigger than the pore size, they will be rejected by means of the membrane. Right? So mostly the rejection is depends on what is the pore size and what is the particle pore size distribution. It depends on what is pore size and pore size distribution, right? Means how it is distributed. Pore range, variety of pore size distribution means the pore size is from 1 micrometer to 10 micrometer or 8 to 10 micrometer. All the pores of what is the range of pore. So this is electrically charged membrane. These are the ceramic membranes. You can see these ceramic membranes, because of the limitation of polymeric membrane is they cannot withstand high temperature, right? And they do not have resistance towards some solvents. They are highly corrosive solvents is there, then they cannot withstand that. So the ceramics membrane, they are come into the picture. They have very high chemical resistance and very high tolerance for the temperature also. So nowadays, for major application where the high temperature is required, these ceramic membranes are used. So mainly membrane material are polymeric, ceramic, glass, metals and liquid fill pores membrane. As I told you, this thin film composite membrane, this blue layer actually acts as a membrane, which is polyamide active layer. See, the thickness is even less than 1 micrometer, zero point 0.0 to zero point 0.2 micrometer. This porous polyether sulfone, which is of 50 micrometer, and reinforced polyester is of around 100 to 150 micrometer. So you can see the total thickness may be around 150, but the actual polyamide membrane, which is act as an active layer of membrane, its thickness is very, very less. So the flux will be higher. So either it is porous, non-porous, dense membrane. If we just say that is the flow mechanism of filtration is mainly molecular sieving, right? And solution diffusion means solution diffusion means if I say, see, in this dense membrane, they are non-porous. So in all other porous membrane, MF, UF, and NF are also slightly different. But this membrane, sieving mechanism, but dense membrane, there is they are based on the solution diffusion. Means if they are not, separation is not, driving force is not based on pore size, separation for the separation. It is based on the solubility difference, or you can say the affinity, right? So in dense membrane, suppose A and B having the same pore, same size, particle size is same, but A is more having more solubility towards the membrane, then A can pass through it but not B, because B is not have any affinity towards the membrane surface. So A can pass through it, A can diffuse through the membrane but not B. So both the same size particle can be also separated by means of the dense membrane, or else based on the difference in particle size, they are separated by means of porous membrane. So RO membrane or dense membrane, their separation is based on solution diffusion. Means what is the solubility of membrane within solubility of solute in the membrane itself, right? So that is solution diffusion. The bigger these small particle, they have bigger affinity towards the membrane surface, though they can easily pass through it, but the bigger particle, they have less affinity, so they will be retained. So here no any membrane is ideal. This is a molecular sieving, bigger particles are retained, only small allowed to pass through it. Generally this Knudsen diffusion is nahi hota hai, molecular sieve and solution diffusion. See, all bigger molecules are retained, only small, which have size smaller than the pore size, they can pass through it. So it is molecular sieving, and this is used in RO. No any membrane is ideal, and here we have shown that exactly cylindrical pore, which is not the case when you prepare the membrane. There may be tortuosity in the pores itself, right? So solution diffusion, some bigger size can also diffuse through the membrane and come into the permeate side. So these are the two mechanisms for mainly all pressure driven membrane separation. This is for the RO, and for the rest molecular sieving. Convective flow means it is for the conventional filters, right? Filter, canvas or what, that where the flow can easily pass through this membrane. Okay. Now, how these membranes are modularized in different pressure vessel, that is mainly of these four types: plate and frame, spiral wound, hollow fiber, and tubular. Plate and frame is same as plate and frame filter press, right? But instead of that filter, conventional filter, it is covered with the membrane. So, right? So on the frame side, your feed is entered. On the plate side, your from both the side of membrane, the permeate collected into the plate and it will come out. So plate and frame filter, which is used for so many applications, right? It depends on which type of application you have. So plate and frame, if you just see major advantage, you can increase the surface area, you can increase the membrane area, you can increase the number of plate and frame, so you can increase the membrane filtration area as per your requirement, right? Detection leakage is easy to identify. Replacement cost is less. If this membrane is damaged, you can take out that frame and plate and replace that membrane, and you can again continue working on it. So that there are some advantage of this plate and frame filter. So very compact, you can, in small pressure vessel, very compact, you can increase the membrane area. Now the main, either it is whatever type of membrane separation process, Pre-filtration is must. You cannot take directly any wastewater or any feed into the membrane. These generally membrane separation processes are used to remove the last traces amount, last final touch, right? Before that, whatever the conventional pre-treatments available that you have to do. Otherwise, the membrane will choke if you not pre-treat your waste, or if you do not pre-treat your feed solution, then it will choke the membrane. It will foul the membrane, so the life of the membrane will be less. So before that, you have to do either whatever the type of membrane you use, whatever type of module you use, you have to pre-filtration, you have to do the pre-treatment to your waste or you to your feed, right? So plate and frame, spiral wound. So pre-treatment is required in most of the cases. Only in tubular you can skip it. Yeah, that tubular module is much bigger in size, so it will not foul easily. It will the fouling or will be not done easily. Right? You can clean it inline, but this type of modules you have to take the shutdown offline cleaning of the membrane. Inline cleaning of membrane is not possible in case of all other modules. So plate and frame modules, where simply filter press, only the canvas simple filter medium is replaced with the membrane, right? Secondly, there is a spiral wound, domestic RO, and all RO applications worldwide. 75% of RO separation processes, they are based on this spiral wound, and rest 25 is based on hollow fibers. But this spiral wound membrane, if you have checked your domestic RO, when you replace the membrane, if you take out that membrane and if you open it, you will see this structure, right? In spiral wound module, there's a central collection tube. See this blue line, that from where you will get the permeate, and this central collection tube, that is the perforated. You can see the perforation here, and blue color permeate is coming here. So this central collection tube, from where the permeate is coming, right? And now see, the feed is coming from this side. ये जो है, this these two membranes are attached to attached to both the sides, and this is a feed spacer, so that there is no channeling. The feed will cover the whole membrane area, and this spacer, where the feed is coming on this surface, this yellow color is membrane, so the feed will allow to pass through the membrane. It will come into this spacer in here in the channeling or permeate space. From this side also, from this yellow membrane, this side also the feed will come, and it come into this. When it's come into here in the permeate channel, it will travel the whole path, because these membranes are wrapped on this central collection tube, right? So they will this, and when the feed is allowed, the feed is entered. Suppose in this second diagram you can see the feed is allowed to pass through it. The permeate pass through this membrane, and this permeate travel the whole path, and finally it reach to the central collection tube through this perforations. And from the second side, you will get from the central collection tube permeate, and outside of the same way this side you will get the reject, that is concentrate, right? So spiral wound module is giving you very high surface area per unit volume, and it can withstand very high pressure also, and it is easy. The compact model you can process, you can make, you can add in series, you can add in parallel this number of units. So spiral wound is most widely in most of the desalination plant, you will get this type of spiral wound module. Second is hollow fiber, where the fibers are very small in size, this capillary, right? They are very similar to the shell and tubes heat exchanger, but instead of tubes, they are hollow fibers. On these fibers are very small in diameter, right? Very small capillary. You can see in this figure, very small in diameter. They will also give you very high surface area per unit volume, but the major problem is fouling. If your this capillary of this fiber is plugged by means of any solute, then that membrane is now, that capillary is not available for the treatment, right? So it is same as cell and tube heat exchanger. Either feed is passed through the inside the capillary or outside the capillary. Means feed is allowed to pass from the fibers or outside the fiber, and it is made up of membrane. So permeation is take place from inside to outside or outside to inside, and you will get the from the central collection tube you will get the reject. Sorry, at the second end you will get the permeate and reject from the based on in your channel, right? This one, the tubular module, compared to hollow fibers, uh, the capillary size is very small. Here the tube size is big. It's around 1 inch, 2 inch tube size, and it is made up of membrane, right? Tube is made up of membrane. It is same as shell and tube heat exchanger, but tubes are bigger in size, which is the wall is made up of membrane. You can see here, feed is allowed to pass through it. This wall is act as a membrane, and the permeation take place from this tube to the outside cell side. So you will get the feed from the cell side and from the tube side, right? So this way, this is again in this the because of larger tube flow, you can have large number of tubular feed flow rate you can accommodate, right? And the fouling chances is less, or in-house cleaning is inline cleaning is possible if there is a accumulation of solute on the surface of the membrane. By means of some chemical treatment you can remove this solute from the membrane surface. So this is feed in concentrate, permeate will come out from the membrane surface. So this is tubular module. Now we'll discuss one by one microfiltration, UF, NF and RO, right? Now I'll commonly discuss MF, UF and NF. MF and UF first. MF are microfiltration. They use porous, symmetric or asymmetric membrane. Thickness and pore size we have already discussed, right? 10 to 150 micrometer thickness, and pore size is 0.1 to 10 micrometer. Pressure difference is less than 0.1 to 3 bar, less than 3 bar. Mechanism of separation in microfiltration is size exclusion or sieving. Based on size, the separation is taking place. And most of the membrane material used for the MF are cellulose acetate, polysulfone, polycarbonate, polyethylsulfone, polypropylene and PTFE. PTFE is polytetrafluoroethylene, right? There are major two types of microfiltration membrane: surface filtration or depth filtration. So in some membrane, they take all the solids at the surface, right? And some membrane, they take some solids into the within membrane itself, within the membrane itself. So the thickness is high in depth filtration. So most of the particles retain with the membrane itself, and in surface filtration, particles retain on the surface of the membrane. It is the same as cake filters and clarifying filters. Those who have studied MO, right, mechanical operation. So it is clarifier. Clarifier, they collect all the particle within the membrane itself, within the filter medium itself. So you cannot predict what is the size of separation take place. Maybe small size, big size particle can be trapped within the membrane, and that will be rejected. You can here predict what is the separation of particle, because the pore size are fixed, right? So if you just see depth filter, ये जो depth filter है, you can range of particle size which is trapped maybe from 2 to 14 micrometer in size. But in surface filtration, you will get the SAR separation. Surface filtration, or it's also known as screen filters. You can say all the 10 micrometer, depending upon the pore size, all the 10 micrometer pore size particles are retained by means of the membrane, and rest all less than 10 can be rejected, can be passed through the membrane. So this is the difference between these two surface and depth filters. We just see the ultrafiltration, same porous membrane used, composite, thin film composite membrane can be used. Pore size is 1 to 100 nm. Pressure difference is 3 to 10 bar, means 1 to 3 bar is up to MF and 3 to 10 bar is UF. Mechanism of separation is same, size exclusion or sieving. Membrane material are polysulfone, PVDF, PN, that is polyacrylonitrile, polyamides, ceramic or cellulosic materials are used. Cellulose acetate, diacetate, cellulose triacetate, all these membrane materials can be used for the ultrafiltration. Right? And the third one is nanofiltration. Nanofiltration, they are slightly different from this MF and UF, because in MF and UF, Microfiltration and ultrafiltration, there is simply porous membrane. But these nanofiltrations, they are slightly charged membrane. And most of the cases, they are neutral or negatively charged or positively charged. So if they are positively charged, then they will interact with the oppositely charged membrane, right? And if the same charge membrane, the same charge particle will be rejected, and the opposite charge can uh, interact with him, and it will affect the performance of the membrane. So nanofiltration membrane have property between the ultrafiltration and arrow, means it is known as ultra osmosis, right? As I told you earlier, but they are slightly charged. So uh, the separation mechanism, they are sieving, they are porous membrane, so it is sieving. They have pore size is in nanometer, 1 nanometer, right? Greater than 1 nanometer. So they are porous. So the mechanism of separation is affected by means of the sieving as well as Donan effects. Donan means the same charge will not allow to pass through it, but opposite charge can pass through it. So that Donan exclusion, that will also affect the performance of the membrane. And when the membrane is slightly charged, and as with the time, this membrane will lose the charge from the surface of the membrane because of so many reasons. Because of there is some change in pH conditions, or maybe some during the cleaning. When you just clean the membrane, nanofiltration or ultrafiltration MF membrane, in any type of membrane, when you clean the membrane after 13-14 hours of operation, when the membrane is fouled, and if you want to clean it, then either it is acid cleaning or alkali cleaning, then acid will also change the surface property of the membrane. So this, because of acid or alkali cleaning, this charge of the membrane will be slowly removed. So when the charge is less, that will also affect the performance of the NF membrane, right? But NF membrane, they have mechanism of separation is not only sieving but also Donan exclusion or Donan effects because of charge of the membrane. Then come to this reverse osmosis. This reverse osmosis we know, right? When we have one side is if we have just one this U tube, and it is separated by means of semi-permeable membrane, means it will allow the only water to pass through it and not any solids. This side we have pure water, and this side we have suppose sea water, concentrated solution. So initially when we just allow the water to flow, means if we keep it as it is, then initially the water from the pure side will flow in this side, and it will dilute this concentrated solution, right? And at the equilibrium, you can say at the equilibrium, because of transport of water in this side, there's an increase in height of this column, right? So this concentrated solution, so this is at one time, this is the difference in H where the equilibrium is achieved, and there is no net flow of pure liquid from this side to this side. Now but this is not desirable. Osmosis is not desirable operation for us. We want to remove, we don't want to dilute this solution, seawater. We want to have pure water, only solvent water from seawater to use as a drinking water or for any other purpose, and we want to remove all the salts. The salinity of seawater is around 35,000 to 40,000 ppm, right? The almost 3.5 to 4.2 weight% of solids are there. So we want to remove that solids, that salts, not want to dilute it. So if we just make the flow reverse, if you want to make this flow reverse, then you have to apply the pressure in this direction, and you change the direction of water from this to this by means of from this to this side, then it is known as reverse osmosis, right? You just reverse the direction of flow on this side, and at that time you have to come, the reverse pressure must be greater than osmotic pressure. Osmotic pressure means what? This membrane is such that it will not allow salt to pass through it. It will allow only water to pass through it. So with high pressure, with increase in pressure on this side, you are forcing water to pass through it, this membrane. So with this force, the salt will also pressurized, and they will also try to go out with this membrane, right, with this from this membrane to this side, but they are not able to pass through it. So what will happen, they will be rejected back by means of the membrane. So they will be they are not allowing to pass through it, so they will be rejected back by means of the membrane. So whatever this concentrated salt, they are not ever allowed to pass, but they are rejected, so they exert some back pressure. They are now from membrane surface to try to go into the bulk solution, and they exert this back pressure. This back pressure is known as the osmotic pressure, right? So this osmotic pressure we have to overcome. If I just say, if the RO is generally operated between 30 to 100 bar, right, 20 to 80 or 100 bar pressure, if we apply here the 70 bar pressure, then maybe this, because of this back pressure or osmotic pressure of this salt, that which is exerted by means of the salt solution, that may be 20 bar, right? So you are giving 70 bar pressure, but the back pressure which is generated by means of the salt, that is 20 bar. So effective gradient is only 50 bar. Effective gradient to push this pure water through the semi-permeable membrane on this side is only of 20, of that difference, right? Hydrostatic pressure difference minus osmotic pressure. So if you just write any flux equation for RO, UF, and MF, the flux is directly proportional to the pressure gradient, that is delta P. And if the proportionality constant is known as solvent permeability constant, because in all the operations we allow the solvent to pass through it, not solute. Our aim is to allow the solvent to pass through it. So the permeability constant AW, that, or the flux JW is equal to AW is equal to into delta P minus delta pi. If it is RO, delta pi is important. If it is UF, NF, and MF, delta pi is not that much significant, because the pore size is so big that they can allow this multivalent divalent salt allowed to pass through it. Even they are having big micromolecules, they retain on the membrane surface, they will not exert that much back pressure. So in case of RO, you have to take this flux is directly proportional to the delta P minus delta pi, means the hydrostatic pressure difference minus what is the osmotic pressure difference. And finally, pressure-driven membrane separation process, that this is the pervaporation. So pervaporation, that is the only process where the phase change is taking place, right? So in that pervaporation, they use which you want. Generally, it is used for the organic aqueous mixture, like acetic acid water or alcohol and water mixture, or having azeotropic solution. They are separated by means of the pervaporation, right? So pervaporation, in pervaporation where the phase change is taking place. So in pervaporation, two types of membranes are used, either organophilic or hydrophilic. Organophilics are those membranes allow only organic liquid to pass through it, and hydrophilic are those which can allow only water to pass through it. So if you want to dehydrate the alcohol, you have to use hydrophilic membrane, which will allow all the water to pass through it and pure alcohol at the reject side, right? So, and here the permeate side is vacuum. We have to apply the vacuum on the permeate side, and this is condenser, cold trap. So feed is heated and it comes to the saturation temperature where it is a mixture of both vapor and liquid. They allow to pass through on the membrane. They allow to pass through on the membrane. So when the vapor, the liquid, saturated liquid come into the contact with this membrane, the vapor, because of the pressure difference, at the permeate side it is vacuum, and it is here it is slightly positive pressure. So permeate allowed to pass through this in a form of vapor. This vapor will be condensed and then it is collected as a permeate. Here it is shown, upside feed is liquid, then there is this membrane. So diffusion of vapor take place, this side vapor will come out, and that we have to condense it, and that will get the permeate. So pervaporation, there is phase change taking place. So it is slightly complicated compared to UF, NF, RO, because in this there is no phase change. Right? Whenever there is phase change, the complication of process is higher. So whatever the processes we have discussed, all the processes, the factors affecting, up to some extent I have already discussed, that performance is affected by means of flux and rejection. like any either MF, UF, NF, RO, or PV. The performance of membrane is judged on mainly on these two parameters. The flux of solvent is given by means of AW, the solvent permeability constant, delta P minus delta pi. Delta pi is the osmotic pressure, delta P is the hydrostatic pressure difference. If this is the membrane, feed water is flowing on this side, and this is the membrane, the permeate flow on this side, right? So what is P1 and what is P2? And what is pi1 on this side, what is the osmotic pressure on feed side, and what is pi2, that is osmotic pressure on permeate side. See, the osmotic pressure is directly proportional to the solute concentration or salt concentration. Jitna salt concentration ज़्यादा होगा, osmotic pressure will be higher. So, and the flux of salt. Some solute will also allow to pass through the membrane. So it depends on what is the concentration gradient on the both the side. C1 is the concentration on feed side, and C2 is the concentration of solute on the permeate side. Some solute will also pass through the membrane. No, and some membranes are available that will give you 100% rejection. But with the time, the membrane performance will, with the frequent cleaning, some membrane structure will change and it will allow some solute to also pass through it. So most of the membrane, they reject almost 99% of salts, more than 90% commercially if we say. But so some solute will also pass through the membrane. That is, if that concentration is C2, then rejection coefficient is calculated as C1 minus C2 divided by C1. So it is known as 1 minus C2 by C1. C1 is the feed side concentration, C2 is the permeate side concentration of solute, right? So this flux of salt or flux of solute is given by means of Js, As, that is the, so flux of salt is depends on directly proportional to the concentration gradient on both the sides. So C1 and C2, that is the concentration, and As is the solute permeability constant, right? So measure these two equations, flux of solvent and flux of salt. Salt flux depends on concentration gradient, and flux of solvent depends on what is the delta P minus delta pi. These are the parameters: pressure, velocity, temperature, concentration, and pH. They affect the performance of the membrane. Pressure, it is a pressure driven, so as you increase the pressure, flux will increase, right? Velocity, if you increase the velocity of the fluid, but velocity will be enhanced at the cost of the pressure. So you have to optimize, right? At given pressure, the velocity will increase. The sweeping means the high velocity will not allow solute to easily settle down on the surface of the membrane. High velocity will take away the solute which is not allowed to pass through the membrane. That solute or that salt can be easily take away or sweep away with the membrane in the reject stream. So it will reduce the fouling. So it will give you the higher flux, right? So temperature will reduce the viscosity of the solvent. So if you reduce the viscosity, the diffusion will be more into the membrane, and hence the flux will increase. Concentration, if you increase the concentration, it will reduce your salt. If you increase this, your salt flux will increase, right? And more salt will give you the more concentration polarization on the flux, and it will reduce the solvent flux, right? If C1 is more, the delta pi will be more. So if your solvent flux is less, but C1 is more, this flux of salt will be higher. So which is desirable or not, that is different for different system, right? pH will change the chemistry of membrane, means pH will alter the, it depends on which pH. All the membrane, they have different pH tolerance, right? Different pH tolerance, different chlorine tolerance. So for different membrane, you have to study that, and for particular feed system, for particular your feed at different pH, how the membrane will behave, right? As I told you that after acid cleaning, some membrane lose their acidity. So after acid cleaning of membrane, if you just have the rejection rate will be decreased, because now the pores is open, so many solute can pass through the membrane. So the rejection is reduced. That is observed in so many experiments, that after cleaning, the rejection is reduced, right? So it depends on which type of membrane we are using. Other factors which affect is hydrophobicity, electrostatic charge, what is the reactive group in the membrane, then what is the molecular weight of solute, what is the charge on the membrane, on solute, what is the shape of the solute, Then what is the membrane morphology? Means pore size, pore shape, pore network, pore size distribution, that means. And the other operating parameter that we have already discussed, right? Pressure, temperature, cross flow velocity, solute concentration, pH, etc. So in pressure driven membrane separation process, why flux decline? I already explained that because of concentration polarization. Concentration polarization, that is reversible and directly occurring phenomena. See, in any membrane separation process, the concentration polarization means accumulation of solute on the membrane surface. So there are various methods how you can reduce this concentration of solute at the membrane surface. So this concentration polarization can be reversed, can be reduced. Its effect can be reduced by reducing the accumulation of or by decreasing the accumulation of solute on the membrane surface. Right? Fouling such as adsorption, pore blocking, and deposition of solidified solute. Sometimes some solutes are adsorbed permanently that you cannot remove by means of any chemical treatment. Some solutes they block the pores that cannot be reversed. Some solute by chemically, some pH change or chemistry of membrane material and your solute is such that they chemically react and make a solidified solute on the surface of the membrane that you cannot change. Either pore blocking, adsorption resistance, and some membrane resistance. This resistance you cannot alter once it is there. But this accumulation of solute, that is concentration polarization, that you can reduce by means of different methods. So if concentration polarization is there, what will happen? It will decrease the driving force, increase the resistance, and permanently damage the membrane. If the solute is retained on the membrane surface for a long time, it will try to interact with the membrane materials and solidify that, and then it will be not permanently removed from the membrane surface. It will reduce the life of membrane, right? This is the phenomena of concentration polarization, right? The Cm, that is the Cm is the concentration of solute at the membrane surface, and Cf is the concentration of solute at the feed. So generally at the concentration is 8 to 10 times higher than what is the solute concentration in the bulk. The bulk stream concentration may be 100 ppm. Here you may found it is 200 to 1000 ppm of solute concentration at the surface of the membrane. These are the various ways that you can reduce the concentration polarization by means of chemical method, by means of hydrodynamics method, by means of physical methods. Hydrodynamics are most widely used because chemical method you have to select very wisely. Physical methods are also used in some cases, right? Chemical methods, either acid or base or sodium metabisulfate can be used as a, or NaCl, HCl can be used as a chemical treatment. Hydrodynamics, you just give the instability, increase the turbulence, or insert some material which will remain inert and not allow solute to settle down on the membrane, or increasing vortices, roughness, or pulsation means you just after some times of operation you give some another pressure pulse, so it will disturb the whole system inside and not allow solid to settle down easily. Those who have already settled, they will also take away with this pulse of high pressure pulse within the system. So that is pulsation, right? So flow in curved channel or curved flow, that is, these are the various strategy to reduce this concentration polarization. Membrane cleaning, because of concentration polarization, flux decline, and once the flux decline, you are giving the same pressure, but the flux you are not getting because of fouling, because of concentration polarization. Then you have to clean the membrane, because otherwise you are wasting the energy, your energy. So cleaning is very important part in any membrane separation process. So either it is a physical cleaning, backwashing, forward flushing, or back flushing, or air flushing, simply by flushing of liquid. During membrane cleaning, there is never applied pressure. During cleaning, we never applied pressure, only simply cleaning of solute from the surface of the membrane. Chemical cleaning it can also be used, like different chemicals, right? But you have to keep in mind it will not damage the surface of the membrane. Then ultrasonic field, in some cases in automobile industry they use this ultrasound ultrasonic or acoustic radiation to clean the smaller automobile parts. The same function can be used here, that membrane deposition on the surface of the solute deposition on the membrane surface can be cleaned by means of ultrasonic field. This is our nanofiltration pilot plant. Right? We have two different modules. This is flat sheet or test cell, which is you can consider as a one plate and one frame. If we have n number of plate and frame here, just stack of that then it is plate and frame filter press. Right? So we have here only one flat, one frame and one plate. In between there is a membrane. Right? You can see this polymeric membrane. So this is flat sheet membrane and this is spiral wound membrane. Right? This is spiral wound. I have already discussed the schematic of that. This show the variation of permeate flux with time. See, with time, as flux decrease with time because of accumulation of solute. This is with the dye, reactive rate dye 198 at 490 kilopascal, means almost 3 kg pressure, right? 3 kg pressure in a flat sheet module. So with time, the flux decrease because of concentration polarization. What I am trying to say, that because of flux decline, you are applying the same pressure 3 kg, but your flux is reduced from suppose 11 to 10 meter cube per meter square per second, then you have to clean it, right? So flux decline with time because of concentration polarization, right? Similarly, the rejection, that is observed rejection with time, that is also decreased with different concentration of dye in a flat sheet membrane at the same 3 kg pressure, right? Rejection decrease means more solute can pass through the membrane now. So it needs cleaning. This is with pressure. It is all UF, NF, RO, they are the pressure driven membrane separation process. So with increase in pressure, obviously the flux will increase. So with increase in pressure of 3 kg, 4 kg or 5 kg, flux will increase. These are the some qualitative properties for the same reactive rate dye solution. If we just take different concentration, see the TDS means the rejection of dye and COD reduction. Rejection of TDS is almost 90%, above 90%, and even COD reduction is almost 97-98% for different concentration of dye solution. Right? Initial TDS is 60 ppm. It rejected 90 ppm. Right? This is a synthetic wastewater, not actual wastewater we have taken. We have prepared into the laboratory by dissolving reactive rate and then we studied. Right? So COD is also reduced. This is a final permeate concentration. Initial TDS is 660 ppm, then permeate will give you only 60, so rejection is 90%. Right? Similarly, variation of permeate flux and with time under different pH condition, as see at different pH, right? pH is 9, see this is the flux, and at pH 5, right? At pH 5 you will get the higher flux because of acid pores are open, maybe surface damage. So and at 9 this alkaline pH. Similarly, rejection is not much affected by means of the pH, but yes, at higher pH rejection will be more. Then permeate flux versus salt concentration. If you increase the salt concentration, then how the rejection will increase? With increase in salt concentration, this is your flux and this is the rejection line. Rejection also decrease. Right? This is showing some AFM images of polyamide nanofiltration membrane. See, initial when the membrane is new, you can see the sharp ridge and valley structures. The surface is very rough, and after the dye solution pass through it, see you can see in most of the valleys these peaks are shrouded, and they are most of the surface is deposited by means of the dyes particle on the surface of the membrane. So in used membrane, you cannot see this sharp ridge and valley structure in this way, right? You can see this is the highest peak, so it is not affected, but otherwise all are deposited with the dye particle in it. So the membrane morphology, that surface properties are also changed because of deposition of solute on the surface of the membrane. Same way, this is for the PANF and PES membrane, means polyamide and polyethylsulfone membrane. This is SEM graph. SEM, with the scanning electron microscopy for the porous membrane when membrane is new, right? You can see the pores, but after the deposition of solute material on the membrane surface, you can see simply all the pores are blocked, right? So this is the for the PES 300, means 300 molecular weight cutoff. You can see these are the pores. Same way for the 150 polyamide, 150, 300, these are the molecular weight cutoff. Means generally in membrane, they are defined in terms of molecular weight cutoff. Means this 150 membrane allow all the particle which is smaller than 150 molecular weight. Means if in this I use an 150 membrane, I will use any dye which is having molecular weight less than 150, then all dye will be allowed to pass through it. But the bigger molecular weight than 150, all the dyes, there is a probability that they will 90% of that dye which is having more than 150 molecular weight, they all are rejected by means of the membrane. Right? So it is polyamide 150 membrane. After the when membrane is new and when membrane is used, what is the change in structure of membrane? That is done by means of FTIR, right? Fourier transform infrared spectrum. So this we have also checked how this ultrasonication. This is ultrasonication bath, almost 35 kilohertz frequency we have used by just keeping this test cell inside this and studied what is the performance of the membrane. So you can see initially at different dye concentration, right? The flux is declined with time. The flux is declined, but when you start after 60 minutes of operation, you can see after this flux decline, but after 60 minutes of operation, we started this ultrasonication bath. So you can see the flux is again revived because inline cleaning of fouling is done. So the flux is again reached to the original level. So this we also studied using ultrasonication bath. If you just keep this ultrasonication continuous, then there is no decline of flux. Means this ultrasonication field is not allowed the solid to deposit on the surface of the membrane. Same way, cross flow velocity. If you increase the velocity, obviously the flux will be higher, right? This is some surfactants we have used, CTAB and sodium dodecyl sulfate SDS. Coating of different surfactants on the membrane will enhance the performance. So we have checked at different concentration, 1, 2, 3 milligrams per liter of concentration of surfactants on the PF. And it is say that as a concentration increase of the surfactants, they will reduce the flux. If you just see the application of membrane separation process, major drinking water, desalination, demineralization, wastewater treatment in textile, pulp and paper industry to recover all the chemicals, dairy industry, beverages, biotechnology to concentrate the protein, enzyme, fermentation broth, biomedical, hemodialysis, right, for the kidney patient, dialysis or hemodialysis to purify the blood, control release drugs, chemical industry, gas separation, hydrogen recovery, CO2 separation, ethanol dehydration, fuel cell, right? If you just see what are the major advantage of membrane separation process, so it is energy saving. In most of the membrane separation process, there is no energy, there is no phase change is taking place, right? All the operations are at ambient temperature. No phase change is taking place, so there is not lots of energy is required. At the same time, clean technology with ease of operation. Technology is quite clean. No further waste is generated, no pollution. It has a potential to replace the conventional technology. Then recovery of high valuable products with minimum efforts can be done. No big instrument, no big equipment is required, right? Similarly, greater flexibility. If I have this pilot plant, if I use I have purchased it for the NF. We have purchased for the nano. We can also perform the experiment on MF and UF because and even with the low pressure RO, right? Because we change the membrane and we change the system operating condition. This can be used for the UF also. So greater flexibility in designing the system. By changing the modules, by changing the membrane, you can have the same experiment with different conditions. Then possibility of hybrid process means you can combine conventional separation process with the membrane separation process. Both you can do simultaneously. So you can do the hybrid. Like pervaporation is used for the separation, dehydration of alcohol. Ethanol, they form azeotropic mixture with the water at 96.4%, right? So when we go for the pervaporation, so distillation is done by means of common distillation. Up to this azeotropic mixture is formed. Then after that, pervaporation can be used to have the 99% pure alcohol. Then limitations, if we just say fouling, so frequent cleaning is required. Upper solid limit means you cannot take directly any solid concentration, any aggressive feed into the system. You have to treat it first and reduce its concentration so the load on the membrane will be less. And finally, it's expensive, right? And if you just say that before passing through this feed solution around 50 ppm, after this passing through the membrane, permeate is almost clean. Almost it will give you 96% rejection of color. Similarly, this is for the molasses water. This is ultrasonication bath, how it works, right? On the membrane surface that we have just checked. That ultrasonic bath, if I just put simple this foil, then within few minutes it will be within few seconds, not damage. If I keep test cell, then you can see this type of perforation, small spin holes, right? You can see these spin holes in the surface. But the membrane, when I put into the flat sheet and inside that sonication bath, luckily the membrane is not damaged. Or nowadays we are doing some research on. Earlier we used to purchase the membrane from the outside, and now we are just try to make our own membrane using polymerization, means interfacial polymerization. And our students, they are doing project. This is our casting machine to cast the polymeric membrane. This is for the PVDF membrane, right? So students, they make the solution. We just purchase the support material from outside and then just cast the small thin membrane, porous membrane, in our laboratory by just means of interfacial polymerization or phase inversion, you can say. If you just keep into the water bath, the phase inverse, and you will get the polymeric membrane, right? Okay. Thank you all. If any questions, I'm ready to take
it. Thank you, ma'am, for such a wonderful and informative session. There are some questions, but looking to the time limit, I'll just take one or two questions from Chemical Engineering Department student Rukank. He has asked how to increase the biogas production from anaerobic membrane bioreactor, treating anaerobic digester sludge with synthetic wastewater as a feed, or the food waste as per using methanol as solvent.
So, first of all, I'm sorry. Actually, I have not done any work in bioreactors.
Okay.
I have not done any work in bioreactors. Simple, I have just one pressure-driven membrane separation process is more. But still, you just mail me this question. I will find out the answer.
Yeah, sure. It's okay.
Madam, you just give me the this question is how to enhance the performance.
Yeah.
Means what is that system? Anaerobic digester of?
Yes. Anaerobic membrane bioreactor.
Bioreactor.
Yeah.
Okay,
fine. No problem, ma'am. Another is which organic solvent is suitable for live cell bacteria viability during making hydrophobic polymeric membrane, PSF based.
PSF. Means
Yeah. It's like hydrophobic.
the
Yeah.
hydrophobic. I understand that they want to use for any hydrophobic system, but
Yes, yes.
I didn't get the question fully, madam, because in
Okay.
that case, which solvent is used, they are saying.
Yes, they are asking for organic solvent.
Organic solvent where you can use this membrane for basically for
Bacteria,
which
life
particular
cells
application.
bacteria, life cells bacteria.
Okay, no
Yeah.
idea, madam.
Okay.
Okay, you
Okay.
can mail me the question. I will definitely try to answer this
Sure, madam.
question.
Sure, sure,
Okay.
ma'am. And one last question, what is the difference between permeable and semi-permeable membrane?
Permeable will allow all generally semi-permeable membrane will not allow specific chemicals. All the membranes are very specific. Semi-permeable membrane allow only water to pass through it.
Okay, okay. Okay, so thank you, ma'am. Thank you for such a wonderful session, and I think the students' concept will also being clear with this session on membrane separation techniques. On behalf of Parul Institute of Engineering and Technology Diploma Studies, Chemical Engineering Department, I thank you for delivering such a wonderful session. Thank you, ma'am.
Thank you. Thank you so much, ma'am.
Yeah.
Hmm.